Okay, we're going to finish up the proof of the midsegment theorem. We have already proven that the midsegment is half the length of the third side, and now we need to prove that it is parallel to it as well. So remember, we're talking about in these first two sentences the fact that these two triangles are similar by the SAS similarity theorem. Well, we know two things to be true about similar triangles. We know that their corresponding sides are proportional, which is what we used to prove the first thing. And we also know that their corresponding angles are congruent. That's what we're going to be using to prove the second part. So this next sentence just says that in similar triangles, we know that all of the corresponding angles are congruent. So we're going to use a couple of pairs of those corresponding congruent angles. So it says, so angle AMN, which is this angle up here, and I'll switch to the notes, it might be easier to see. AMN is this angle right here. That is an angle of the small triangle. Which angle of the large triangle does it correspond to? It corresponds to this one right here. It's the one that has this side that corresponds to that one and this side that corresponds to that one, making it up. So this angle AMN is congruent to this angle, which is called angle ABC. Likewise, angle ANM, which is this one right here of the small triangle, would have to be congruent to this one down here of the large triangle, which is angle ACB. Now, what type of angles are those? Remember, those angles are called corresponding angles. And we learned the converse of the corresponding angles theorem says if the corresponding angles are congruent, then what must be true about these sides? They must be parallel to each other. And so now we have proven both parts of the midsegment theorem. We proved that MN is half of BC and that MN is parallel to BC. So that is known now as the midsegment theorem. Now in question 5, we have some segments that are dividing our triangle, but this time they are not going to be midsegments because we don't have any midpoints. We do, however, know that we have some parallel segments. FG, DE, and BC are all parallel to each other. So we're going to name the triangles on number 5 in your notes. There are 3 of them, and we are going to describe how they are related to each other. So up at the top of this figure, we have a triangle, and we would name that triangle, triangle AFG. So you have triangle AFG. Then we have what I would call the medium triangle here, and that would be called triangle ADE. And then we have the large triangle, triangle ABC. Since all of these segments are told to us to be parallel, remember we have those pairs of corresponding angles that are congruent to each other. We also know, of course, that angle A is congruent to itself by the reflexive property. So what is the relationship among those 3 triangles? Well, I hope that you would know that these triangles are all similar to each other. So I'm going to put a similar symbol in between each one of them. Now, how do I know they're similar? Remember, we have those shortcuts. Which shortcut did I use when I only talked about the angle measures? I used the AA similarity postulate to say that those triangles are similar to each other. So that is question 5. So when you have a segment drawn parallel to a side of your triangle, you're creating 2 similar triangles. But we just saw when we had an additional segment that was parallel, we had a 3rd similar triangle that was formed. So it really doesn't matter how many segments you have parallel to a side, you're creating that many similar triangles. So the sides of those triangles, remember, would have to be proportional because that's what it means to be similar. But what about the pieces of the sides of the triangle? Let's look at this animation to help us here. Now, right now, this really isn't a triangle, is it? But the same relationship exists if these lines are parallel to each other. And the reason for that is that I could extend these lines and they would eventually cross, making a triangle, right? So even if we look at a figure and it doesn't appear to be a triangle, remember the same properties hold true because these lines would eventually intersect, making a triangle. So let's look at these relationships. So again, we're creating the parallel relationship and maintaining that, and I want you to look at the proportionality that is correct here. This part, AB, compared to this part, DE, has the same ratio as BC to EF. So the parts are proportional to each other. So that is our conjecture on number 6 in our notes. We are going to write the fact that if a triangle is cut by segments that are parallel to one of the sides, then the other two sides of the triangles are cut into proportional parts or segments. So if a triangle is cut by segments, so FG and DE on this figure are both parallel to the side, then the other two sides, that means this side AD and this side AC, are cut into proportional segments, meaning 3 over 4.52 is equivalent to 3 over 4.52 is equivalent to 4 over 6.03. They are all equivalent ratios. So you can pause this and write this as number 6 in your notes. That is our conjecture. Now, we just talked about this, can we use properties of equality in similar triangles to help us prove this conjecture? So once we prove it, remember it's going to be a theorem, and the name of this theorem is called the triangle proportionality theorem for obvious reasons. We're proving the proportional parts of a triangle. So this is a fill in the blank on number 7 in your notes. And so the given in this triangle is that parallel relationship between this segment and the third side. And that's super important. That's what allows us to have this proportional relationship to begin with. So it says, that's the given, because we know the given is true, that FG and BC are parallel. And remember, you can show parallel by drawing arrows on those segments. Since they are parallel, then I know angle AFG, this angle right here, is congruent to angle ABC, and AGF, this angle here, I'll use 2 arcs this time, is congruent to angle ACB. Now, how do I know that to be true? Well, what type of angles are these? They're corresponding. So that is the corresponding angles, and they put postulate. It's a theorem. We can prove it, so either one is fine. But just know it's the corresponding angles relationship that we're looking at there. That's enough information to say the triangles are similar. So here we have a similarity statement saying triangle AFG, the small one, is similar to triangle ABC, the large one, by which shortcut? Well, all we have is 2 angle pairs, and so obviously that's the AA similarity postulate. Now, by definition, similar triangles have 2 things that are true: corresponding angles that are congruent and corresponding sides that are proportional. We're obviously filling in sides here. So in the denominator, we have AF. AF is a side of the small triangle. So in the numerator, I better have its corresponding side of the large triangle. Now, on your test, some of you are not showing that you understand what we mean by corresponding parts. This side of the small triangle, AF, does not correspond to this side over here, the large triangle, AC. They do not correspond to each other. They're not on the same side. It also does not correspond to BC. The side that corresponds to AF is over here on the same side, but it's the large triangle side. It's AB. So that's what has to go in the numerator here. Now, this is large triangle side over small triangle side, so the other ratio is set up in the same consistent manner. Large triangle side AC, and now I want to put the small triangle side that corresponds to it. So AC is over here on the right side of the figure. It corresponds to AG, the small triangle side. Now, using the segment addition postulate, remember we have a segment addition postulate and an angle addition postulate, and all it says is the parts add up to the whole. So AB is my whole. What are the parts that add up to get AB? That is AF and FB. So AB is equal to AF plus FB. The other side, the AC is the whole, the parts are AG and GC. So AC is equal to AG plus GC. Now, by substitution, we can go up to our proportion and replace AB with AF plus FB. And we can replace AC with AG plus GC. So we're just substituting those equivalent expressions there. Now, this sum written over this denominator can be split up into two different fractions. So I can split up AF plus FB all over AF to just be AF over AF plus FB over AF. Just write them as two different fractions. And the reason why that is helpful is because this AF over AF simplifies to just the number 1. Same thing here, AG over AG just equals 1. So since we have a 1 on both sides of our equations, we can subtract it away, and we're left with simply FB over AF equal to GC over AG. Notice FB is this part over AF, which is this part. And it's equal to GC, which is this part, over AG, which is this part. And again, that's the triangle proportionality theorem. Now, we've talked about this already. Do we think that this conjecture holds true only for parallel segments of a triangle? And the answer to that is no. We looked at this example here that we know eventually those two sides would intersect, making a triangle. So it doesn't have to be a triangle, just it would have to make one eventually if the sides intersected. So number 8 on your notes says the two transversals will eventually intersect, and so this is just another example of parallel lines intersecting a triangle. Even though we're only seeing a part of it, we're not seeing the complete triangle. Now, on your homework tonight, we'll go ahead and talk about this wrap-up question too. It says, how would the perimeter of a triangle and the perimeter of the mid-segment triangle compare? Remember, perimeter is just a sum of the side lengths. You're just going around the sides and adding them together. So it gives me the lengths of the mid-segments, and so I could easily find the perimeter of the mid-segment triangle by just adding 7, 8, and 3, which is 18. And remember, we learned today that the mid-segment is half of the parallel side. So that means AB would have to have a length of 16. And we could go around filling in the other sides. If this mid-segment is 7, that means AC has to be 14. And if this mid-segment is 3, so side CB is 6. That makes every mid-segment half of its parallel side. So now, if we add up the lengths around that side, we would get 14 and 6 is 20 plus 16 is 36. So we got 18 for the perimeter of the mid-segment triangle and 36 for the large triangle. So do you see they also have that 1:2 ratio that the mid-segment has with the third side. All right, so I want to talk just a moment about your homework. Number 6, I would recommend that you draw a figure on that one. That would definitely help you answer that question. I want to point out the fact on number 7 that segment JM is not a mid-segment. Notice these parts are not congruent, so do not try to apply the mid-segment theorem to find the length of JM. On the other problems you'll find in your packet, the very next sheet is Help with Assignment 13.1. So really make sure you refer to this as you look at these problems, and that should help you get started on those. All right, good luck.